What I plan to do in this video is give you guys a brief introduction to vectors and cross products. I'm just going to revise in a very non-math intensive way what vectors are and how to do a cross product. First of all, a vector, it really just defines a magnitude and a direction. And not only that, but let's say, for example, we have a pond, something like that, with a boat traveling, let's say, 5 meters per second, a magnitude of 5 meters per second in this direction. And this direction is denoted by, let's say, 30 degrees to the horizontal. So I've drawn that just there. Well, we know that this piece of information just here, a boat traveling at a magnitude of 5 meters per second at 30 degrees to the horizontal, can be recharacterized as it's traveling in a vertical direction and a horizontal direction simultaneously. In fact, we can use simple trig to know that if it's traveling at 5 meters per second in 30 degrees to the horizontal, that's the exact same thing as it's traveling vertically 5 sine 30 meters per second vertically, and it's also the same thing as saying it's traveling horizontally to the right 5 cosine 30 meters per second. Vectors become really important here because you can simplify this by saying, let's say, the velocity vector of the boat can now be resummarized as 5 cosine 30 and 5 sine 30 meters per second. Just by general notation, the first element here will always denote the horizontal displacement, and the second element here will always denote the vertical displacement. Engineers will often concern themselves with only three dimensions or less. Even though a vector could, by definition, have n dimensions, but we're not interested in that. In fact, if we were to be particularly honest with ourselves, there would be a zero component for the z direction in which the boat was traveling. There are many practical applications to using vectors in statics and in dynamics. For example, if we were interested in describing, say, a force vector, which I've drawn over here. Right now, this is just this blue arrow denotes a vector. Let's call it the force vector, which has a component not only in the horizontal direction, in the vertical direction, but also in the out of page direction. As a result, let's say that this is just an arbitrary example, but let's say the horizontal component of this force is actually, let's say, 3 newtons here. Let's say the vertical component is, say, 5 newtons. And let's say the out of page or z component or k component is actually 7 newtons right here. As a result, you can redescribe this force vector as 3 newtons here, 5 newtons here, and 7 newtons here. Notice how each of its components are separated into each of these elements. In fact, if you wanted to go one step further, you can then redescribe it as, using basic linear algebra, we can say that's the same thing as 3 times by 1, 0, 0 plus 5 times 0, 1, 0 plus 7 times the vector 0, 0, 1. These things are identical to each other, but the beauty of recharacterizing this equation just over here is that you can make a simplification for this unit vector right here. Notice that this unit vector just here only has a component in the horizontal direction. Engineers denote this as the I unit vector. Basically, it's a unit vector 1 unit long purely in the horizontal direction. That is the I unit vector just here. This is by definition the J unit vector, and this right here by definition is the K unit vector. I corresponds to X, J corresponds to Y, and K corresponds to Z. So now that's the vectors pretty much all done. There's a lot more to know, but those are the basics for what you're going to need to know in statics. The other thing that's really crucial to learn for statics is cross products. So for example, let's say we have an arbitrary vector A. This is an R3, meaning that it's got 3 components. Let's call those arbitrary components A1, A2, and A3. A1, A2, and A3 are scalars. They're just numbers, but each of these numbers correspond to a particular direction in the, like for example, A1 would just denote the magnitude of the vector in the x direction, and A2 would denote the magnitude of your A vector in the y direction, etc. And let's say we've got a second vector B, which I'll denote as B1, B2, B3. Purely by definition, and I won't go into the formal proof as to why it was defined this way, but by definition, the cross product between vectors A and B is given by the determinant of your unit vector I, your unit vector J, and your unit vector K in the first row, and then your scalar A1, A2, A3 as your second column, and your vector B1, B2, B3 in the third column. I won't go into the formal proof and how determinants were defined or anything like that, but I will show you briefly how to solve something like this. What you're meant to do right now, and I'll go into a little bit of insight into why it was defined this way, but I won't go into the mathematics of it too much. But what you're meant to do is first start off with your I just here, write it down just here, I, and then take the determinant of, actually imagine drawing a solid line straight horizontally and vertically through the I, and then find the determinant of everything left. That's the way I've always imagined it, so you can imagine that as I times the determinant of A2, A3, B2, and B3 subtracted from the J unit vector, and imagine you draw a line straight through here and here, and then take the determinant of everything that's left. Those would be the 2 elements on the left and the 2 elements on the right, and that would be A1, A3, B1, B3, and then get the K unit vector. Now we've done I, we've done J, we're on K. Take the determinant of everything that's left. If we were to draw an imaginary line through there and there, would take the determinant of everything left in there. So that would be A1, A2, B1, B2. And if we were to solve this out, that would give us I times by A2, B3 subtracted from A3, B2, all subtracted from J, A1, B3 minus A3, B1, right? It's just this times this subtracted this times this plus K unit vector times by a1 b2 subtracted from a2 b1, and we can just quickly simplify that a little bit more as one giant vector. We can write that as a2 b3 minus a3 b2, and then in the j component it will be a3 b1 minus a1 b3, and over here it'll be in the z component or k component, it'll be a1 b2 minus a2 b1. That is our cross product of A cross B. Notice that your answer is not a scalar, it's another vector. And the beauty of this vector is that it was defined such that it is orthogonal to both vectors A and B. So for example, if we had two vectors A and B, let's say, I'm just going to draw them here on this two-dimensional page, vector A here and vector B here, our A cross B vector will be orthogonal to both of them. It's going to be tough for me to draw on this two-dimensional page, but imagine that this is perpendicular to both A and B. So this is just going to be your A cross B just here. And I'll try and show you that that's orthogonal just there. Righto. So the way you can tell whether A cross B, because notice that there are two vectors which are orthogonal to both A and B. One's this one and the other one's down here as well, right? The way you can tell that is from the right hand rule. Imagine having your right hand stuck out and you've got your thumb just here, and then you've got your index finger pointing that way, and you've got your middle finger, I can't really draw this too well, but it's pointing kind of out of the page, and then you've got your other fingers just there. This denotes, this is going vertically up, is your A cross B. This, your middle finger kind of pointing sideways, it can be either A or B, it doesn't matter. A and B. And notice that A cross B by definition is going to be orthogonal to both A and B. This is important. This is purely a mathematical construct at the moment, but it's also important for defining moments as well. Just like vectors are really important for describing forces. Anyway, that's a little bit of intuition and a little bit of a non-mathy way to describe the cross product and vectors. Sooner or later I'll go into how they actually are used practically, and we'll go through a couple of examples.